Hello, my name is Scott Lindstrom, and this is a training on NUCAPS Soundings in AWIPS. I'd like to acknowledge my co-authors that are listed: Chris Barnett, Rebecca Ismaili, Emily Berndt, Tony Reale, and Dan Neatfeld. This was updated in February of 2022. NUCAPS is an acronym, NOAA-Unique Combined Atmospheric Processing System. You might be asking, what's combined? Well, on NOAA 20, it's a combination of infrared information from the CRIS, the Cross-Track Infrared Sounder, which has 1,305 channels, and microwave information from the ATMS, the Advanced Technology Microwave Sounder, which has 22 channels. NOAA 20 is sun synchronous. It's passing over the equator at 1:30 and 13:30 local time. That means it's passing over the East Coast at around 5Z and around 17Z, over the plains and over the Great Lakes around 6Z and 18Z, and along the West Coast around 9Z and 21Z. That's plus or minus 1 hour each day. There's a satellite downlink both at Svalbard and McMurdo. Then the data is processed and moves through several different satellites before getting into the SBN and getting into the WFO. So it takes about 60 minutes for the data to show up in your AWIPS station. How are these vertical profiles produced? It's a two-step process. First of all, there's a regression that statistically relates the information in all of the sounder channels to a description of the atmosphere. That's using coefficients that were derived from a few focus days. Initially, those were one for each season in 2014 and 2015, and that creates a first guess field that's also used for cloud clearing. Note that the regression uses all the sounder and microwave channels, so all 1,305 CRIS channels, all 22 ATMS channels. Those are used to create a first guess estimate of what the atmosphere looks like. A retrieval is then generated, which, like most retrievals, minimizes an observation minus calculation value. The first guess is related to climatology and the surface pressure. And then there's an iterative process where you sequentially solve using a radiative transfer model for new estimates of what the radiance in the atmosphere looks like, and you compare it to the observed radiances. The final sounding is computed on 100 levels. That's the standard number of levels in this particular radiative transfer model. It's really a lot more levels than are warranted by the sounder resolution. Cloud clearing is an important aspect of NUCAPS because where you have clouds, that's typically where the infrared retrieval will fail. The microwave retrieval typically fails where there is precipitation. But cloud clearing is tricky because you have 9 CRIS observations within each NUCAPS profile. If you have uniform clouds over all 9, it's pretty easy for the cloud clearing to say it's cloudy there. You're not going to get a good retrieval. So what does clear versus cloudy look like? That's kind of shown here, where we have scenes in the upper left that look, fairly cloudy, but they're not cloudy enough. There are enough clear regions in between the cloudy regions that you get 1 or 2 CRIS fields of regard. The 9 CRIS fields of regard are contained within 1 ATMS footprint. On the bottom right, you see regions that are too cloudy. So even a region that has very thin cirrus, that is going to be designated as cloudy, and you're not going to have good retrievals. So here's what the 9 fields of regard look like across a CRIS scan. First of all, that the CRIS scan does not extend to the edges of the VIIRS scan. So it's not quite as wide as a VIIRS swath. And you'll also notice that when you're looking straight down, so field of regard, that's what FOR stands for, field of regard 14 in the middle has smaller footprints than the ones out on the edge. How does a retrieval work? Well, this flow chart might help you understand it a little bit. It's a lot of complicated math, but you start on the left-hand side with a first guess, then you account for any biases, if there are any in there. And then on the right-hand side, you see an iterative loop that's using the radiative transfer model, where you're using that model to calculate the transmittance, You use the model to compute radiances, and then you compare the computed radiances to what is observed. If there's a difference there usually is, you adjust the profiles and the skin temperature and then recompute the transmittance. And you keep doing that until you converge to a solution. If the residuals are small enough, you have a success. And if there are too many cycles, you fail to converge. And for infrared, you can have too many cycles where it's cloudy. And for infrared and microwave, you can have too many cycles where it's precipitating. You don't use all of the channels in the retrieval. 399 out of the CRIS channels are used for physical retrieval. So not all of the 1,305 are used. And you use different channels. So there are 24 different channels in green that are used for surface temperature. There are 87 channels in black in the upper figure that are used for atmospheric temperature. There are 62 channels that are used for water vapor. How do you choose which channel to use? You're not using all 1,305, you're only using 399, and you're using ones that are what are called spectrally pure. So if there's a region in the electromagnetic spectrum that is sensitive to both carbon dioxide absorption and, for example, water vapor absorption, that kind of channel would not be used. You want to be able to discriminate between effects due to water vapor only and effects due to carbon dioxide only. What kind of information is most useful from a NUCAPS profile? Mostly it's water vapor in the mid-troposphere. You do not get a lot of added information about temperature, mostly because temperature is pretty well forecast. But the water vapor distribution is much harder to initialize and move forward in a model successfully. The water vapor data from NUCAPS is going to give you added information that can be useful. So here's just a list of the strengths, the gradients, how things are changing in time. NUCAPS also gives you great information out over data voids, such as oceans. The vertical resolution of NUCAPS profiles, however, is much smoother than radiosondes. So don't expect them to look the same. And you should always compare the near surface values from a NUCAPS profile to the actual observations at the surface. What's the effective vertical resolution? That's what the DOF here is. That relates to the number of layers that are resolved by NUCAPS data within the troposphere. NUCAPS profiles are smooth. You only see 6 to 10 layers of temperature, maybe 4 to 6 layers of water vapor. Keep that in mind. You might ask yourself, well, why don't I just use data from a numerical weather prediction model? Well, as shown here, convection can develop in a model where it's not observed. Wouldn't it be better on the left-hand side to use observations from a satellite rather than the erroneous features that are going to be in the model? NUCAPS is available in AWIPS under the Satellite tab. Underneath Satellite, there's typically a SUMI NPP and NOAA-20 menu item. And if you click on that, you'll see NUCAPS sounding availability and also gridded NUCAPS. If you click on NUCAPS sounding availability, you see something that looks like this. We have 3 different colors of dots. Swath of points will typically show up about 60 to 75 minutes after the pass. So these 1913 UTC points probably showed up somewhere around 2015 to 2030 UTC in AWIPS. The green dots are regions where both retrievals have completed successfully. Where you have yellow dots, this is typically where you have cloudiness. The infrared retrieval failed, and the red dots are where infrared and microwave retrievals have both failed, typically where it's raining. I like plotting these over satellite imagery so you kind of know what to expect. So if I just toggle between the 2 of these, so green, mostly clear skies, yellow, mostly cloudy skies, red points are where precipitation is most likely. That's a lot of data to process through. I mean, you could click on each of these individual points, look at them, and then close out N-sharp and look at the next point. Typically, when I do that, I forget which point I looked at. But you can also use pop-up SKUTs, which are under the volume browser. You click on that, and then you right-click on the image to click on NUCAPS as something you're sampling. Then you also turn on sampling. And then when you mouse over, you will see the small SKUT that shows up. This is for a point over Indiana. And here's the one just to the south, to the southwest, a little bit farther to the south. And then we jump even farther to the south So it helps you scan through things. You can look for thresholds. You can see where gradients might start or end. It's a useful way to get a quick look at what the data are showing before you click on the actual point. So here's just an example of 3 points off the coast of Oregon. This is plotted on top of a day-night band image. We have a region in clear skies. Notice how smooth it looks. We have a region that's near the edge of clouds. And I guess there's some indication there that it's getting a little bit closer to saturation in the lowest levels. And then we have a red point in the deep precipitating clouds. And you notice you have a profile that doesn't look very useful, at least at the lower part. You still have good information about where the tropopause is, for example, because that's above the precipitation in the clouds. Each day, there are 4 consecutive passes over CONUS. There's an overlap, typically north of 40 north. There are slight gaps south of 35 north, where you'll get no data for that particular 12 hours. The path locations shift eastward about 1/3 of the path width from one day to the next. So this image that's centered over Georgia on this particular day, the following day it would be centered maybe over eastern North Carolina. What do consecutive soundings get you over Pennsylvania? One at 17Z, one at 1830Z. There was a slight risk. So it was well timed. You could get an estimate of what the thermodynamics looked like at these 2 points, at 17Z and at 1830Z. And you see how the LCL is changing. You see how the mid-level inversion is getting a little bit weaker. That might inform your nearcasting because you see that the stability is decreasing, and that might help you be a little bit more confident in assessing whether or not the convection is going to maintain itself. Here's a second case. This was a case of enhanced probability of severe weather over the Midwest. And we had a case where we had 2 consecutive passes. The earlier shown here, this is from 1747Z. We're looking at the total totals index using gridded NUCAPs. So there are gridded NUCAPs that are available in AWIPS. You might remember that these are located just under NUCAPS sounding availability in the menu. And then we had another pass at 1932 UTC, where we have a continuation of the diagnosis of instability over Wisconsin, mostly over the southern part of the state. You can also see the red points over Iowa, where the convection has started. You'll notice where the severe weather was. So the diagnosis over the southern part of the state was reflected in the storm reports on that particular day. This slide shows gridded NUCAPS field. So the thermodynamic profiles at each of these points are interpolated in the horizontal, and then you can compute thermodynamic fields. It's a much more efficient way of viewing all the thermodynamic information that's in the NUCAPS profile. I've mentioned that it's useful to compare the NUCAPS profile values near the boundary to the actual observations at the surface. NUCAPS profiles have been examined at the hazardous weather testbed for several years. Here's an example from 2015 where the forecasters are saying, well, you really have to modify the surface to make it more amenable with the observations that you see. So you get a better estimate of the true thermodynamics associated with the profile. How do you edit these? Here's an example from February of 2022, where we're looking at this point on the Gulf Coast of Florida. You'll notice it's in a region where the temperature and dew point are around 81 and 60. Here we have a temperature at the surface of 26 Celsius and a dew point of 17. So do they match the observations in the METAR? Not really. Hit edit graph. You'll notice it's toggled to off right now. It's going to toggle it to on. You notice these draggable points that show up. And what you can do is you can move those points around so that the sounding is a better match to the surface observation. So here we have what it looks like after I've changed the values. I've made it a little bit warmer and a little bit drier. If you don't like what you've done, there's a reset button you can use. So I toggled the edit graph on, moved things around, and then toggled the edit graph off. And you see the changes that I've made to the plot. Not very big. Mostly I've dried out the bottom of this profile to make it match what's going on at the surface. You can see how it changes the LCL and the LFC. And in the readout box, you can see how it changes the different CAPE and the different SYN that are associated with this particular profile. You can also use the edit data box. So going back, there's an edit data box that you can click on. That brings up boxes, and I've changed a variety. You could change a variety of different levels here and actually enter in the value you want to be there. Here's kind of the classic example of how you can use NUCAPS. This is from Dan Neatfeld, who was a Sioux in Omaha at the time. So we have a 1915 UTC visible image with a broken cumulus field and a GFS that says, oh, it's going to rain. So the question for you is, will you see afternoon and evening convection on this particular day? And there was a NUCAPS overpass at that time. So we're just going to be looking at this particular green point. And here's what the profile looked like that particular day. It matched the surface METARs fairly well. We have very low CAPE. And the question is, would you expect convective development here? Probably not, and nothing happened. A couple of days later, Omaha was in a high risk. In the box, in the inset there, we have all the storm observations. So large hail, widespread wind and hail, and a couple of tornadoes. And we have NUCAPS profiles from that afternoon as well. And I want to draw your attention to the dew point gradient here. First, we're going to look at this point that's been boxed in green. That's near the northern edge of the dew point gradient. And when we look at that profile, this one was modified so that the surface temperature and dew point are more in line with what was seen. And you have this surface-based CAPE of 1850. So we looked at this point in the green box, but recall that there's this very nice dew point gradient. So if we look at the point that's just to the south of that, what do we see? This is an unmodified one with a surface-based CAPE of 686. And if we modify it to look probably a bit more well-mixed, as was observed, and the surface temperature and dew point are adjusted to what is observed, we have a much higher surface-based CAPE, up around 3100. So you know where the gradient in CAPE is for this particular example. And it's frequently seen that convection will run along a CAPE gradient. Here's another example where we have sequential passes over the upper Midwest. And the question is, will the convection develop? The upper two maps show NUCAPS profiles at the northern edge over the UP and over the southern lower peninsula. Notice how the profile is different. As you get farther and farther to the south, you have a much drier air mass. So this might inform you on, is that convection that's forming over northwest Wisconsin into the western part of the UP, is that going to develop to the south as it moves off to the east? And based on these NUCAPS profiles, maybe you're going to tell yourself, well, not very far to the south, because once you get really far to the south here, you have very dry mid-level air that's going to prevent any deep convection from occurring. And then we have another pass around 19Z, which is shown on the bottom. So again, we have a region just to the east of this developing line where kind of the same story is being told. At the northern terminus, here we have a fairly moist air mass. Looks moist adiabatic, so you might expect convection to develop in that region. But farther to the south over southern Lake Michigan, you have a much drier looking air mass. It's a little more moist than it was, 90 minutes earlier, but this kind of information can help you decide how this convection might be evolving over the course of the day. So just a quick summary. Only NOAA 20 passes are in AWIPS right now. You can actually create NUCAPS with any combination. It's, as I believe it's called, satellite agnostic. You could do this with MEDOP, which has EASI and AMSU on it. But that data, those kind of data are not in AWIPS. You can find them online. This is produced with every polar orbiter pass, and the time latency is about 60 minutes. Maybe 10 layers, temperature layers, and about 5 moisture layers. So it gives you a fairly smooth view of the atmosphere. Learn how to modify the soundings if the lowest layers don't agree with nearby METARs. NUCAPS tells you much about the state of the atmosphere's thermodynamics, especially gradients and how things are changing. So if there's something where you need to know about the thermodynamics, whether it's moisture in low levels, the freezing level, cold air aloft, NUCAPS gives you useful information. I've shown you where NUCAPS data are in AWIPS, but they are also available online. There are gridded NUCAPS fields available from this site from Sport. You can also find gridded NUCAPS in Real Earth, and you can find NUCAPS profiles at this NESDIS star OSPO link. That's all for now. If you have any questions, my emails are listed. Send me any question you have, and I'll try to answer it. Thank you for listening.